All right, so let's do this problem. This one is a little bit challenging, but at the same time, not, oddly. We want to find the internal shear force and bending moment as a function of x. First of all, you'll notice that it's a continuous load, right? The whole length. So that means we only have to write one set of equations. That's a good sign. The more challenging part will be that if I do make this cut at x, if I look at the left side, what kind of load do I have? Trapezoidal. I look at the right-hand side, what do I have? Trapezoidal. So there's really no advantage there. Left side, I do have a reaction. Right side, I have a reaction. So it looks like it's just a squared deal. No advantage. However, the left side will all be with x, whereas the right-hand side, if I looked at that, is going to be 18 minus x. So that little dimension will be a little more challenging to deal with. So I'm going to go to the left side. When I go to the left side, I just need to find the reaction at A. So let's start with that. So I'll draw a free body diagram of the structure. And I'll assume at A, which is a pin, I have positive shear at A. So I'm going to start writing my reactions in terms of shear. Okay? So on the left side, positive shear is up. So on the right side, positive shear is down. Now this load needs to be broken up into a rectangular portion and a triangular portion. Let's do the rectangular portion first. So the area of a rectangle is base times height. The height is 1 kip per foot. The base is 18. So I'll have a load of 18 acting through the centroid of the triangle, which is right in the middle. Since I'm going to try to find A, I'm going to make all my distances from B. So that'll be 9 feet from B to the centroid. Now the next part is this triangular piece. I've seen this happen quite a few times. Students will come over here and use the height of the triangle as the total height of of all the distributed load, which is not true, right? Remember, this part is 1 kip per foot, so that means this change is 2. So when I do 1/2 base times height, I'm going to get 1/2 18 times 2, so I'm going to get, again, 18. And that force will be the centroid of the triangle, which from B is 1/3 the distance. 1/3 of 18 is 6 feet. So with that all said, I want to find my shear at A. So if I sum the moments at B, I should be able to find my shear at A. Who did I leave off on? Who's up next? Oh, Ms. Pinafore, what do we got? About B. Positive 18, right, because right-hand rule, right? So 18 is the first one. What's its moment arm? This one. What about the second one? Right. And then what's left? Right, so this force is creating negative moment times 18. So what's that equal to? The shear at A is, looks like 15. Is it 15? Yes?
Yeah.
And it's positive, so it is a positive shear at A. Okay? So now let's do a free body diagram of that piece. I'm going to try to make it a little bit bigger so we can see it. because I'm going to have, and I'm exaggerating the distributed load just so you can see all the pieces. So I know at this end that load is 1 kip per foot. I just found my shear, which is positive, and that's 15 kips. I'm making this cut at some distance x, and then internally I have positive shear and positive bending moment. Now first, what's going to be the intensity of the load at this point right here? I'll call it W, and it's going to be a function of x. Can I write an equation for that line right there? Well, remember, a straight line, it's the old form. In our case, it will be W is equal to AX plus B. A is the slope, B is the intercept. So at x equals 0, which is right here, what's the intercept value? 1. So that means that B is going to be equal to 1. What's the slope of this line? Rise over run. Well, the rise is it goes from 1 to 3, so that's a rise of 2 over a run of 18. 2 over 18 is a ninth. So W is going to be equal to x over 9 plus 1. Does that work? When x is equal to 0, what do I get? 1. X equals 0, 1. What's the value at x equal 18? Should be 3. 18 divided by 9 is 2, plus 1 is 3. It works. Now, if this part is 1, what is this part? Which should be this minus 1, right? That should be x over 9. Everybody see that? So this part is 1. This part is x over 9. You add them together, you get, it should work. So with all that, I can now find my forces. I think I'll do it this way, just so it won't be so jammed in there. I'll call the rectangular force F1 and the rectangular force F2. So what is F1 equal to? Base times height, which is just x, right? What's F2 equal to? Well, it's a triangle, so it should be 1/2 base, which is x, times height, which is x over 9. So if you expand that, you get x squared over 18. Everybody see that? And this is the distance d1 from the cut to the force. This is the distance d2. What's d1 equal to? Should be half the distance, which is x over 2. And what's d2 equal to? Should be 1/3 the distance, right? Which is x over 3. Easy, right? So what do? Make sure it's in equilibrium. So let's do that. So I'm going to sum the moments at the cut and make sure it is in equilibrium. Ms. Dasgupta, do that for me. Do the moment. What's the internal moment here? Positive or negative?
That is negative. No, it's positive.
It's positive.
Positive and...
Before you go all the ones, F1 and F2, are they positive or negative moments?
Positive.
Okay. So do F1. What's F1?
So you have plus x squared over 18.
Oh, say that again. I'm sorry.
What do we do?
F1?
F1 is x.
Okay, and then this distance is?
It's x over 2.
Correct. Now do the next one, sorry.
So you plus x squared over 18.
And what's its moment arm?
X over 3.
Correct.
And then we also have the 15, which is negative.
And what's its moment arm?
X.
Correct.
Yeah.
So all of that should have the units of kip feet. So if I solve for the moment, what do I get? Well, I'll just put all those to the other side. I'll put them in order. So this term here is going to be x cubed over 54, I think. Is that right? And then this term here will be x squared over 2. And then bring that, oh, that's negative, sorry. And then plus 15x. Do I know the moment anywhere in this beam?
Yes.
Where? At x equals 0, which is A, what's the moment? What's the moment at a pin? 0. When I plug in x equals 0, does this equation give me 0? It does. What about at B? Should be 0, so somebody check this and see that if you put in x equal 18, do you in fact get 0? No one, oh, everyone's clicking away. It's kind of a long one. I'm going to start to put a check sign there.
Like a 0.
All right. I think it's 0 too. Cool. All right, so let's do the last one. The shear, and we finish with this problem. So I'm going to sum forces in the y direction. Make sure it's in equilibrium. Mr. Mabry, you're up.
Yeah, negative shear, negative B.
Yep, negative b.
Minus x squared over 18.
Okay. What else?
Minus x.
Minus x. That's F1 and F2. What else?
Plus 15.
Plus 15. I think we've accounted for everything. So if I solve for the shear, it looks like I get minus x squared over 18 minus x plus 15. And that should be kips. Well, we have this relationship that we've kind of discovered, that the derivative of the moment should be the shear. If you take the derivative of the moment equation, do you get the shear equation? Looks like that's a yes, so that's a good sign. We also know that the shear at x equals 0 is, we solve for it, 15.
15.
Does our equation tell us that it's 15 at x equals 0? It does. What is the shear at B? Well, we didn't solve for it. We never solved for By, did we? But our equation should tell us. So if I put in x equal 18 there, I should get the shear for B. I don't have anything to check with because we didn't do the calculation. Okay. Any questions about that? All right. See ya.